general relativity, step by step. Last time I spent some time looking at how much proper time an object takes, how much wristwatch time an object takes to fall from a finite radius down to r equals 1 or indeed r equals 0, and we showed that that was finite. And I've got my little diagram, my Schwarzschild diagram here. We've got a Schwarzschild diagram here with ingoing light rays, and we'll see that light rays apparently don't cross the horizon at all, yet the proper time for an object, and I've got non-null geodesics here, I've got an object dropped from a distance here. These objects apparently don't cross the event horizon here, yet they take a finite amount of proper time to do so. And this caused a huge amount of confusion when the theory was being developed back in the 1920s. So how do we deal with this? Well, what we want to do is to create a new set of coordinates that allow us to talk about what happens when r approaches 1 and gets less than 1. So what I'm going to do is I'm going to go back to our old friend the Schwarzschild metric. Just open that up a bit. Just go up to a clear space. We've got ds squared equals 1 minus 2m 2gm over c squared over r. Let's minus that dt squared plus, and of course I'm going to choose 2gm over c squared equals 1. That's my unit of length, and I'm also going to choose c equals 1. So ds squared, my line element squared, is minus 1 over r dr squared. Sorry, that's dt squared, plus dr squared over 1 minus r, plus r squared d omega squared, which I'm going to set to 0 because I'm considering radial coordinates. Now if we have ingoing light, we know that ds squared equals 0 on a null geodesic. So that tells me that dt squared 1 minus 1 over r equals dr squared over 1 minus r. And so we know that dr by dt squared equals 1 minus 1 over r squared. Is that the right way around? Yep. So dr by dt equals plus or minus 1 minus 1 over r. And of course the plus and minus correspond to the ingoing and outgoing light direction, so that's the red and the blue lines on this diagram here. Great. So we've got dr equals, we'll have the negative ones, equals minus dt 1 over 1 minus r. So we're going to choose the negative line there, so we're going ingoing. So what does that mean? That means that minus t plus a constant which I'm going to call p equals the integral of dr over 1 minus r. They're equal, so minus t plus p equals the integral of r over r minus 1 dr. Subtract 1 and add 1 on the top there equals the integral of 1 plus 1 over 1, no, r minus 1 dr, all in brackets, equals r plus log of, sorry, it's the modulus r minus 1. Minus t plus p. Now this thing here is the integration constant. And the clever bit is to use that integration constant as a new variable. So I'm going to use p as a new variable. That's nice. So what does it look like? P equals t plus r plus log mod r minus 1. Notice this works for anything except r equals 1 itself. We can have r being greater than 1 or less than 1. So long as r is positive, I guess. We're always going to assume that r is positive here. So that tells me that dp equals dt plus dr times 1 plus 1 over r minus 1 equals dt plus, and that's r minus 1 plus 1, so it's r over r minus 1 dr, or I guess I'll write it in a better format. Dr equals, dp equals dt plus 1 over 1 minus 1 over r dr. Now what I'm going to do is to take the Schwarzschild metric and rewrite that in terms of dp. So I can say that dp sorry, I can rewrite dt equals dp minus 1 over 1 minus 1 over r dr. So I can say that dt squared equals dp squared plus dr squared over 1 minus 1 over r squared minus 2 times the cross terms. dp dr over 1 minus 1 over r. Well, that's nice. So now I can write, ooh, where's it gone? Excuse me. Where is it? Oh, here we are. So I'll go back to my Schwarzschild metric equals minus 1 minus 1 over r dt squared plus dr squared over the same thing. And I'm just going to substitute for dt squared, and I've got that here. I'm just going to substitute this equation into there and see what happens. ds squared equals minus 1 minus 1 over r times dt squared, which equals dp squared plus dr squared over 1 minus 1 over r all squared, minus the cross terms, 2 dp dr over 1 minus r, plus this term that was here all along. I've just taken that's dt squared, which equals these three terms here, times the minus 1 minus 1 over r, plus dr squared over 1 minus 1 over r. And lo and behold, that term cancels with that one. Isn't that nice? So where does that leave my Schwarzschild metric? That says that ds squared equals minus 1 minus 1 over r dp squared plus, because a minus and a minus is a plus, 2 dp dr. And this is a perfectly sensible metric in P R space. I'm going to stop there because I think that's quite nice. Notice it's not diagonal. Normally, well, it's much nicer if you have Gij equals 0 if I is not equal to j, and that's not the case. We've got these cross terms here, so it's a non-diagonal metric, which will cause us a few problems later. However, the Eddington Finkelstein coordinates are very nice in other ways. So I'm going to stop there, and I'm going to develop this and talk about it in the next screencast. Stop.